So this will be the last chapter for Organic Chemistry 2, and we're going to be looking at, no surprise, more carbonyls. But this is sort of where it all culminates. All the different carbonyl sort of chemistry you've been learning is kind of leading up to this point. And really a lot of the stuff we've learned overall in Organic Chemistry 1 and 2. So this might be like a slightly more challenging chapter, and we're going to be looking at a lot more mechanisms than usual. But this is a good place to kind of end it, because it sort of really is going to cement and test our knowledge in some ways for this last chapter here. But the essence of this chapter is, as the title implies, these condensation and quote-unquote alpha substitution of carbonyl compounds, and we'll take a closer look at what that all means, right? And so you notice here we have this this quote-unquote reaction here that might look a little similar to something we've seen before, but the essence of this chapter is going to revolve around this keto-enol tautomerization. And this is just a sort of fancy way to say that when we have a ketone like this, right, keto, it can undergo this process called tautomerization, where it can become the enol form. And to remind you, we've seen this before in our alkyne chapter. When we were trying to make alkynes into carbonyls, it went through this process. So make sure you remind yourself of that as well in that alkyne chapter. But the keto form is usually much more stable than the enol form, which exists 1% or less of the time. However, this is important, right? This process is important, this tautomerization is important, and we'll of course see examples of why that is. But this is something that rapidly happens in solution, usually with water present. Okay, so we'll usually be including this a lot in our reaction errors from now on. The enol tautomer, however, can be more stable in certain situations. Again, tautomer is just referring to the enol form specifically. Okay. If we had a scenario where we have a diketone, this dicarbonyl, we actually end up getting a reverse situation where the enol form, quote unquote, is actually more stable. And as we go through the chapter, we will definitely see this example again. Right, one of the ketones has become, right, our enol here, or alcohol there, and there's this hydrogen bonding going on between that hydrogen and the adjacent ketone. So this is more stable, right? And it's stable due to a couple reasons. Due to the six-membered ring that gets formed, right, with the hydrogen bonding. And, right, resonance, because now we can do resonance with that adjacent ketone, right? So this actually exists about 76% of the time. And I'm not going to ask you math questions or anything like that, but just to give you some actual numbers of what actually is seen in reality, okay? So this tautomer, this enol tautomer, is more stable in this case. However, usually it's impossible to isolate the enol. So in reality, if we were to run a reaction to try to isolate this thing, we wouldn't really be able to. So how does this process actually happen, right? You notice the keto-enol, they have some different connectivity. This is not resonance, right? This is very different than resonance because we're actually moving atoms around, but they are actually constitutional isomers, right? They have the same number of atoms, there's different connectivity. And so how does this transformation happen? So it happens a little bit like this. So if we're using that same keto up there, again, R just meaning any number of carbons or hydrogens. And again, we're doing this tautomerization here to go to the enol form. The actual mechanism looks something like this. We're going to do things sort of concerted here, where with the presence of water, it undergoes this transformation where we're sort of getting that proton and moving around our electrons here. right, to get to our enol form, like this. Okay, and this process can happen right in reverse. Again, as written, it doesn't really go heavily in reverse, but it still does go in reverse, and the mechanism for that looks like this, where the H2O is grabbing that acidic proton off of our alcohol, and our double bond is grabbing our hydrogen from H2O, and so we can go in reverse now. The big difference between these two, right, one being right, the keto form is more stable, but the keto form, right, is electrophilic at the carbonyl carbon, right, and it is acidic at the alpha carbon hydrogen, right, meaning right, this hydrogen is acidic, and then the carbonyl carbon, right, is electrophilic. And for our enol form, right, it's nucleophilic at the alpha carbon and acidic at the alcohol hydrogen. Right, so it's nucleophilic at this carbon, right, because that is the carbon that is doing the grabbing of the proton from the water, and then it's acidic at that hydrogen, right? And we'll explore this more as we go through, but this is the general essence of this reactivity, right? The enol form is going to be again, less stable, but it does undergo this sort of reactivity where it's more nucleophilic and it's acidic at the alcohol carbon. Okay, so enolates. So enolates, as the name kind of implies, right, similar to enols. Essentially, all this really means is that it's a negatively charged enol, right? And is deprotonated at the alpha carbon. So what does this alpha carbon terminology mean? So you might have seen this if you've taken any biology courses, or if you're in any biochemistry related classes. This will come up again too. This terminology, alpha, is referring to the carbon that is directly adjacent to the carbonyl. As we go further out, right, this would be a beta carbon, this would be delta carbon, and this would be gamma carbon. Okay, so the alpha carbon is referring to, make this nice and red, right, the alpha position, right, the carbon directly next to the ketone. And the enolate, right, this form here is less stable, but it undergoes resonance. Right, this is not tautomerization, this is resonance to get to this more stable form here. Right, because remembering our resonance rules, right, the oxygen prefers to have the negative charge, right? So what does this reactivity look like, right? If we had an actual ketone here, and we treated it with some sort of strong base, right, we're looking at our alpha carbons, we would end up, right, removing one of those hydrogens, right, in just an acid-base reaction to get to this enolate here, right, which undergoes, again, resonance to get to its more stable form. Right, so this is more stable, and this initial form here, right, with the carbonyl still present, this is the reactive form. right? So even though, right, this is the major resonance contributor and it'll look like this most of the time, when we actually start doing reactions with enols and enolates, this is going to be the reactive form, right? Which is interesting, right? Because this is the more stable form, right? But for it to actually react, it needs to undergo this change to get to the reactive form. So this leads to unique reactivity of with enols and enolates due to this resonance issue, quote unquote. And we'll see examples of this as we go through, okay? And so when we're talking about strong bases, what exactly do we mean? Right, because we've talked a lot during Organic Chemistry 1 and 2 about what makes something a strong base or the existence of a strong base. So let's go ahead and actually look at a real example of this and kind of cement some things down. So when we're generating enols, when we're generating enolates, we need this to be particularly basic, okay? Which is why we need the pKa to be something that is above 30, right? Remember, a high pKa can, quote unquote, can mean basic. Okay, so all these things, these high pKa's are indicative of these being strong bases. LDA, which we've seen before, is a particularly strong base because it is because of negatively charged nitrogen, but also it's a poor nucleophile, which is sometimes what we want, right? It's a poor nucleophile, but a great base due to steric bulk, right? It has these big, bulky alkyl chains here. So as an example, right, let's have this ketone here. We have our hydrogens present, and if we were to make an enolate, and let's use, just for the sake of ease of drawing, right, let's use this nitrogen here, right? It's going to come in, grab one of our protons off of the alpha carbon, and we're going to get to our enolate here. And so, right, 2 hydrogens remaining, we have, right, a lone pair there, negatively charged, right? And of course, right, it is undergoing resonance as well. So we do also have the existence of the more stable, quote unquote, resonance form, right? However, if we want to do selectively, right, how do we make a selective enolate? We can do that with an example like this, where instead of having a singular carbonyl, we now have 2. And I'm going to draw in these hydrogens here, right? Now we have multiple alpha carbons, right? We technically have an alpha carbon at each of these carbon spots here. And what's important to know, and this might be a reminder from Orgo 1, right? These hydrogens next to carbonyl, they have a pKa of about 20. And these hydrogens here actually have a pKa of about 9, right? So this is more acidic than the hydrogen at the end here. So if we were to expose this di-keto to a weaker base, so an O-, this ethoxide is actually a weaker base, we actually get the following enolate, where the negative charge is there and not something in the middle, right? Because this weaker base can grab one of these hydrogens, right? Getting to this as our enolate. right? And this is more stable. Hopefully you recognize this because, right, we have, right, multiple resonance forms instead of just one, right? Instead of just making this like singular example like above, the lone pair in the middle here can go either to the left or right to make multiple resonance forms, right? And using a strong base, right, or a stronger base, would lead to side products or potential side products, right? Because a stronger base might end up taking, right, kind of either hydrogen, or will go after both over the course of the reaction. Using a weaker base ensures that it only goes after the lower pKa, right? However, you might be seeing that O-, right, you might look at it and say that should be a strong base, right? And while that's true, we have to remember that these enols, or sorry, these hydroxide O- bases, right, are a little less basic, right? So these weaker bases in this case is referred to things like O-, OH-, terbutanol 2, right? These are slightly weaker than these nitrogen examples, right? So while they're still they're strong bases, they're weaker than these nitrogen bases, okay? Just something to keep in mind. And we'll see more examples of this as we go forward with the notes, okay? All right, the last thing I want to talk about here is some actual reactions using enolates. So if we're looking at our first example here, we're going to look at halogenations, okay? And all the reactions we're looking at for the semester, we'll be dealing with alpha carbon for the most part. So the alpha carbon in this case, right, is here. And so with any sort of halogen, right, X here being halogen of some sort, right, X equals Br, Cl, or iodine, not necessarily fluorine though, we can generate a reaction where we can attach halogens to that alpha carbon, right? And so we can do that through a couple different ways. We can either do it through an acidic mechanism or basic. And so the acidic mechanism looks like this. And we'll use HBr for first example here. Right, we're going to generate, through this acid-base reaction, this sort of more reactive carbonyl. And then we go through this tautomerization, where, and I'll show the mechanism briefly, where we have some sort of base grabbing, right, one of these protons, right, to go from the keto form to the enol form. Right, so it's important to recognize that when we're doing a tautomerization, right, see we've made that enol, and so now we can do our reaction with Br2, which goes through this sort of mechanism where the lone pair in the oxygen goes back down, right? We're reforming our carbonyl, and our alkene is grabbing one of the bromines from Br2. And when we do that, right, we're almost at the end of the mechanism. We have now our bromine, right, is on that alpha carbon, and the last thing we have to do essentially is just get our reaction neutral. So get rid of that pretty acidic proton that's on our ketone. Right, something to really note here is that, right, remember I had said earlier that the enol form, or sorry, the form with the lone pair at the end is more reactive, right? We have to go through this transformation here, right? This is an important transformation because this is the more nucleophilic carbon, right? And so reforming that carbonyl and pushing the electron sort of all the way down is this important intermediate that we have to go through, or process to go through, in order to get that carbon to be nucleophilic, right? This carbon here has to grab that bromine because of this process, okay? And we'll touch on that more, but reforming that carbonyl is sort of important, okay? The basic mechanism is shorter, and we go through the actual enolate. You see up top, we didn't actually ever form the enolate. We went through tautomerization, but we didn't form any sort of enolate. So if we used OH minus here, we can grab that proton, right? And we're going to push all these electrons over to get to the more stable enolate form. Right, remember this is the more stable enolate form. And when we react with Br2, right, what we're doing, right, the O minus isn't grabbing the bromine, but instead, right, we're reforming, right, the carbonyl, and then the alkene is reacting with the bromine here to get to our final product, right? We're reforming the ketone. We are using the alkene to grab the bromine, right? We're making, again, like we just described, the process of pushing down these electrons is important because this carbon here needs to be our nucleophile, right? It needs to be the thing that's grabbing the bromine, right? So this final air pushing is important for sure, okay? All right, so let's look at one more example here. I know this video is a little bit longer than usual. So let's look at this last example here called the haloform reaction, which is essentially what we just did, except we're doing it 3 times. So we're doing 3 halogenation reactions. Okay, so to give an example, say we just have this ketone here, and we're using 3 equivalents of I2, and then 3 equivalents of NaOH, right? So to remind ourselves, right, these are undergoing these basic conditions, right? And what we end up doing, right, is we go through this process of making this carbon, right, nucleophilic several times over, right? We have our base, right, grabbing the acidic proton here, going through this enolate, and then attacking the I2, right? This process happens multiple times, and we get to the final product here, where we've essentially replaced all of the hydrogens with iodines. And now, this is a great leaving group. This is a great leaving group due to the carbanion stabilization. And with that, right, we have this great leaving group. We can undergo hydrolysis, right, which we learned about in the last chapter, or multitude of reactions, really. Where we can have an OH come in, attack that carbonyl, and then now this CI3 is a great leaving group, right? So we could turn this into carboxylic acid, and right, our leaving group has left. This iodoform, right, which is the non-IUPAC name, but where the name of this reaction comes from, the haloform reaction, so we generate this iodoform. So this is just a way we can take a ketone of some sort, do this reaction with it, do this reactivity with it, and have something useful occur, right? Where we can make something like, because before, right, this reaction would not undergo, right? We can't go directly from a ketone and do hydrolysis, right? Because we need to make a good leaving group. So making this a good leaving group and then doing hydrolysis is a totally valid and viable pathway. Okay, in a class we're going to look at more examples of tautomerization, these halogenations, to get ourselves used to seeing these things. Because I know, right, this is a longer video than usual, but right, I wanted to make sure we had a lot of examples to go through. So we'll take a closer look at more of details in class. Okay.